Hello everyone, welcome to this lesson. So in this lesson we're going to go through the Python code for the bisection method. If you remember, the bisection method is a bracketing method where it actually chooses an upper limit and a lower limit to get an approximation for the root. Now the upper limit here and the lower limit are an average to get the root, as in this equation that you see here. What we did is in the previous lesson, we actually applied this on the function x squared minus x minus 2, and we took the upper limit and lower limit as 1 plus 2.5, and we took an average of these, and we had our first root as 1.75, and we found that compared to 2 we have a 12.5%. The second step that we did is we wanted for the second application to find where the root is, and the root is where there is a change in sign, and we find that there's a change in sign here, and if there's a change in sign here, the root here becomes the lower limit, as you can see here. Then we applied the same equation here for the bisection, and we got a better approximation of 2.125, and we have an error of 6.25%. Again, we found where there is a change in sign to know which interval to deal with next, and we found that it's actually the left interval, which makes the root here the upper limit of the new section. And we applied the same thing for the bisection method, and we got the new root of 1.9375, and this gave us an error of 3.125%. So you can see three different iterations got us to from 12.5% to 3.125%. Now, in this lesson, we're going to be developing a Python code that can get you an estimate for whatever error you're interested in, whether it's 0.1%, 0.01%, or 0.001%. And we're going to be playing around with different error criteria. Now, let's begin. This code is actually very, very simple code. Here I have put the function. I define it using a lambda expression, so f is equal to lambda x colon x squared minus x minus 2. So this is the equation or the function that we have up here. I have defined the initial guesses here, xl for the lower limit, so xl here is 1, xu, which is the upper limit, is 2.5, and then we're going to go here for a few initializations. Here, since this is a loop that is going to be depending on a criteria of an approximate error, so we're going to keep looping to get a better approximation, just as long as the error in this case is above 0.1%, and we're going to just initialize it here as 100. Here I is equal to 1. This is going to be kind of a counter that is going to be counting the number of applications of the bisection that we're doing. So for this case, I'm going to be starting the counter at 1, so I is equal to 1, and I'm going to have a code here that keeps increasing I by 1 to count how many applications I'm actually doing the bisection. And the xl here, I'm just going to call it that my first approximation is the upper limit, which my first approximation is 2.5. Here, this is a normal print function that is going to seem, this is the header as you see here. The I is the number of application of the bisection, and for each application I want to know what the approximate error is, the true error is, and the corresponding root. So actually, let's begin the actual main loop of the bisection. Given that I have the upper and lower limit, what I'm going to do is I'm going to get my first root, so upper plus lower divided by 2. And given that I have my new root, before I go to the next iteration, I need to figure out what is my new interval that houses my root. So what do I mean by that? So if you remember here, we have this example here. We found that our new approximation was 1.75, and we know that our root is in this interval on the right. So we're going to be creating this f statement to find where our root is, and we're going to use a multiplication of functions. So we're going to say if the function at the root, which is here, is multiplied by the function at the lower limit, which is here, is less than 0, in other words, it's negative, because if there is a change in sign, the multiplication of the functions is going to be negative. Because if there's no change in sign and both functions are positive, that's going to give you a positive answer. If both of them are negative, that's going to give you a positive answer. So the change in sign is going to be an indication or indicated by a negative of these two function values, or multiplication of these two function values. So if I multiply, say, these two, and I get a negative, that means my root, that means my root is here. That means the xr here becomes my upper limit, and you can see here that the xr is going to be stored in the upper limit. But if this is actually not a negative, it means that this interval houses my root, which means my xr is no longer the upper limit, but in fact the lower limit. So we're going to say else xr gets stored into the lower limit. So here this is a f statement just merely to create our new interval for a new iteration. If the function at xr multiplied by the function at the lower limit is less than 0, then make the xr the upper limit. If that's not the case, makes xr the lower limit. So once I've created the upper and lower limit for the new interval, now before I go to the next iteration, I'm going to create the approximate error. So if you remember the approximate error, we're going to take an absolute here. It's the new minus the old divided by the new. So xr minus x old divided by xr, all multiplied by 100 since we're dealing with percentage. And also we're going to be creating the true value since we have it, which is 2 minus the current approximation divided by 2, all multiplied by 100. And of course, before we go to the next iteration, we have to store our current approximation in x old before we create a new approximation here, so we can later create or calculate the approximate error. And you can see here, this is the string format that's going to output the application of the bisection, corresponding approximate error, corresponding true error, and also the corresponding root. And before also I go to the next iteration, I'm going to up the I, which is the application of the bisection, by 1 every time. So let's actually run the code. So you can see actually it's a very, very simple code. We define the function here, the upper and lower limit, a few initializations. We created the XR. Then after we created XR, we created our new upper and lower limits, created the current approximate and true error, stored the current approximation in x old, upped the I by 1 before we went to the next loop. So actually, let's go ahead and run this code for 0.1% and see how many applications of the bisection is going to take for us to reach this error. So you can see here we have 10 different applications of the bisection method. We started here approximate error of 42.85, and we went below 0.1 by 10 different applications. And you can see here the root is 2.000488. So we definitely converged to the root of this equation. And you can also see that the first one was 1.75, the second one 2.125, the third one 1.9375, as we have presented in the previous lesson, these three, and with also the corresponding errors, as you can see here, 12.5, 6.25, 3.125, and so on. So let's actually examine a few other error criteria. So if I do, say, 0.01, I run this, it's going to take 13 different applications of the bisection to go below 0.01, and you can see 1.999939, and we can keep doing this for maybe 0.01. If I run this, it's going to take 17 different applications to reach this level of accuracy. So it went below 0.001 at 0.000572. Now, if you see, we actually have another different here root at -1. So let's actually find this root. So how about we use maybe negative, say -1.5 and maybe 0 as our upper and lower limit for the -1, and use this code to find it too. One other change I'm going to do is also the true error. Put it in terms of -1 and see how many iterations it's going to take to actually get to an error of 0.1. So actually run this. So 11 different iterations, and you can see it's -0.999756, and we in fact went below 0.1% at 0.0732. Let's see if I do 0.01, how many applications is that going to take? Okay, 14 different applications to get to there, and you can see here we converge to our root of -1.000031. So you can see these approximations are almost identical to the true value, and these techniques are extremely simple, and it was merely an averaging of an upper and lower limit. So you can see the effectiveness and the simplicity of these numerical methods. Let's actually do the last one at 0.01. So 18 different applications of the bisection method. We went through, we went below 0.001 at 0.000572, and almost identical to the true value, -1.000002. So you can see it's a very, very effective technique to find the roots of an equation, just using an upper lower limit and knowing the function and also this equation of the bisection. So just want to recap a little bit briefly. The really two aspects of the bisection method is basically finding the root using this equation and also identifying the section where the root exists using this if statement, if else statement. You've been aware of this error in storing the root for the next, or storing any approximation for the next iteration and all that. So these are more standard lines of code for most numerical methods, but these are the two that are unique for the bisection: the equation for the bisection and identifying the section where the root exists. So you're going to find also this is going to be common for the next technique that we're going to be introducing, the false position, and you're going to find that also for future sections or future methods. Basically, we're going to be just changing these two pieces of code. Well, that's it for this lesson, and I will see you in the next lesson.